Hi there. Welcome to Chain Rule Day 3, where we just practice the hell out of it. Um, ooh, I have a note here that we must go over 64 from the homework. Huh, what's 64 from the homework? It says attached, but I don't have my textbook with me. I'll get this. Oh, wow. That's some freaky kind of tough love. Okay, let's take a look at this problem. I hadn't thought anything would be this interesting. um, y equals c over 1 plus a e to the minus bx. It's our dear friend logistic function. Okay, I'm going to flip this up. Please note, that is not going to change because I'm taking all of this and flipping it up. So I'm going to have c constant times 1 plus a e to the minus bx raised to the negative 1. Now here's the thing. See that plus sign? You can't apply this negative 1 to each of those. If you do, that's the same as being this student who says, oh, that's going to be equal to x squared plus 4, at which point you cry. Because you know that that student was supposed to FOIL this out. And when they do, they get this stuff, but they also get 4x. So I'm not going to apply that exponent to each of these, just like I'm not going to apply that exponent to each of these, because I see that plus sign. If that was plus or minus, I can't apply. If it's a multiplication symbol, yeah, I can apply. All right, so this is our logistic function, and what about the derivative of the logistic function? Well, let's go. I think the question here must have been something about uh, when does this have an inflection point? When is the second derivative equal to 0? So let's see what happens when we explore this. Okay, I need to take the derivative of a constant times this step. So I'm just going to keep it constant. I'm going to bring down the power. I've got this 1 plus a e to the minus bx. Don't forget to subtract 1 times the derivative of the inside function. Well, the derivative of 1 is 0. I don't have to worry about that. The derivative of a constant times e to the is that constant times e to the times the derivative of what's up here. Okay, so it's minus bx. So what can I do here? Well, I guess I can think. But this looks good to me. I probably want to put these together. And I think that the minus here and the minus here are going to turn out to be, because like these are just things multiplied together, so I can write a b e to the minus bx, and I can take that negative, I'll come with this negative, and just have c 1 plus a e to the minus bx to the negative 2. So there's my y prime. What about y double prime? I know. Look, it's a product rule. So this times the derivative of that. C1 plus a e to x 2 times the derivative of that. Well, the derivative of e to the is e to the, and the derivative of e to this stuff is going to be e to this stuff times the derivative of stuff. These are just constants, so they're going to be there as well. But I need the derivative of that stuff, and I get negative b. Yes. Think about this as being e to the 2x. The derivative would be e to the 2x times 2. All right, are we done? No, that was just the first half of the product rule. This times the derivative of that. Now I need that, a b e to the minus bx, times the derivative of this, c times negative 2, 1 plus a e to the minus bx Don't forget to subtract 1. Yeah, it's around this time that people forget to subtract 1. Times the derivative of this inside. The derivative of 1 is 0. The derivative of this constant times here is going to be all that stuff times the derivative of here, which is negative b. Now, remember, I wanted to find out when y double prime was equal to 0. We know that y double prime equal to 0 means, well, often is an indication of an inflection point where the function goes from concave down to concave up, or concave up to concave down. So let's see what we can do to simplify this a little bit, because it looks like an awful lot of intimidating stuff today. So that b, I thought I got rid of that negative. Looks like I'm going to have a positive b. Yeah, let's just think about this again. Okay, so we started off with 1 plus a e to the minus bx to the minus 1. This was our original problem. And I said, okay, constant, bring down the negative 1, leave stuff alone, subtract 1, times the derivative of the inside of the stuff. Derivative of the inside stuff is 0 plus the derivative here will be a e to the minus bx times the derivative of that inside function minus 1. So where did that negative 1 go from bringing that down? Okay, and then the derivative of this is that. Okay, do I have anything there? Oh, no, no, no. Sorry. Yep, got confused with comparing f with f prime and with f double prime. That's unfortunate. Starting again, y prime equals negative c1 plus e a e minus bx to the minus 2 times derivative of the inside a e to the minus bx times the derivative of the innermost. So all of these things are multiplied together. Minus times minus is plus. So I'm going to have a, b, c, a, b, c, negative is positive. 1 plus a e to the minus bx to the negative 2 times e to the minus bx. Okay, there's y prime. Now, what about y double prime? So, again, I have the product rule. I have all this stuff times the derivative of that. C 1 plus a x to the negative 2 times the derivative of e to the stuff. Derivative of e to the stuff is e to the stuff times derivative of stuff plus this thing, e to the minus bx times the derivative here. Now, this is all constant. So we just have a, b, c, and then the derivative of this, bring down to negative 2. I leave the inside stuff alone, and I subtract 1 times the derivative of the inside, derivative of that is 0. The derivative of a times e to the stuff is going to be a times e to the stuff times the derivative of stuff. Okay, so now what can we type? Well, this is the place where it's really good that we spent all that time thinking about how many terms we were looking at. There's one term. Here's the other term. See how they're separated by that plus sign? So what's my GCF here? What can I take out of each of these terms? Well, I see an ABC. I see 1 plus a times e to the minus bx raised to different powers, so I'll take out the smaller power. And I definitely see an e to the minus bx. Ooh, I see a couple of them here. I'm just going to take out one. So I'm taking out, for y double prime, taking out a, b, c, and I'm taking out a 1 plus a e to the minus bx to the negative 3, because the negative 3 is smaller than negative 2, and I'm going to take out an e to the minus bx. You know, negative 1. I had this problem the last time. So that negative and that negative made me positive. Okay. But I did discover here, when I take the derivative of this, that I'm going to minus b. Here in the second term, I have minus b. So I think this becomes minus the b squared. All right. So what else do we got? We've taken out that, taken out that. We took out that here, here, here. And we took out the smaller of power, so this is all gone. But when I factored in negative 3, I ended up with this to the positive 1. So I have 1 plus a e to the minus x, this. And then our plus sign, because everything else cancels out, our plus sign times x, cancel this, cancel this, cancel this, cancel that. I still have this, and that. So minus 2 e to the minus 3x. Whoa. Can I combine like terms? Sure, I can combine like terms. Wait, where did I make it? After the plus sign. That negative here, and that minus 2. Now they are like terms. Now I can combine them. One of these minus 2 of these is going to be negative 1 of these. Negative 1 minus 2. Oh, that's very exciting. Now comes the time. Now remember, we were trying to find out where the inflection point was on this logistic function. This is all constant. I'm looking for y double prime equal to 0. These are just constants. A b squared c equals 0. Yeah, 4 equals 0. No, you don't have to worry about that. But this, and this, and this, I need to set equal to 0. Okay? Well, let's think about it. This is an exponential decay curve. This is never equal to 0. So I really only have to worry about this. Okay? So let's take a look. I've got 1 minus a e to the minus bx, and I wonder when that equals 0. So I'm going to move this stuff to the other side and say 1 equals a e to the minus bx. I'm going to have 1 over a equals e to the minus bx. I'm going to take the ln of both sides so I can break this down. So I have ln of a to the negative 1 equals negative bx. And if I divide by negative b, I get x equals ln of a to the negative 1 over negative b. Okay, what is that? Well, that's the place. Oh, actually, I could do this interesting thing where I brought this power down, cancel it with this power. So now I've got ln of a over b. This is the place where y prime is equal to 0. So, but wait, let's take it a little further. What about this piece? I need to be setting this piece. This piece. Oh, that's just one. What? Oh, hold on. I want to show you something interesting. By the way, this, um, there's so much going on in this one. I've got 1 over 1 plus a e to the minus bx raised to the third. And I want to know when it's equal to 0, right? I'm setting all these factors equal to 0. Well, the first thing I do is to clear out that fraction. 0 times stuff, yeah, sorry, that's 0. So I end up with 1 equals 0, and that's not going to happen, so this doesn't play any role. This is the one that tells me when x is ln of a over b, I have y prime equal to 0. Okay? or y double equals 0. Now I want to go back to y equals c over 1 plus a times e to the minus bx. And I want to take this x and replace it with what we just found, ln of a over b. So it's at this x value when this is supposed to have y double prime equal to 0, perhaps even an inflection point. So let's see if I put that in there, what comes up. Y equals c over 1 plus a e to the minus b times ln of a over b. Now, do you see? And so now we're looking at c over 1 plus a e to the minus ln of a. I'm actually going to take that and put it up there. Why? Well, look what happens when I do. 1 plus a e to the ln of a to the negative 1. E to the ln passes. So now I have c over 1 plus a times a to the negative 1. Well, what do I do when the bases are the same and I multiply? I add those exponents. 1 plus negative 1 is 0. A to the 0 is 1. And look what we've got. Do you remember at the beginning of the year, we did that worksheet where I asked you where is the rate of change greatest? And I said, this point here, the slope looks most positive. And we said that if this was y equals L, then the y value there would be L over 2. And I said, I can't explain to you yet why that is. Well, look what we just proved. We know that this is the carrying capacity of this logistic curve. So we have y equals c. And we just found out that inflection point, this time we're going from positive up to positive down, happens when the y value is c over 2. And we already know that x value. That x value is ln of a over b. This we never really talked about. We never knew where that x was. What we said if we wanted to find this point is we would graph our logistic function in y1. In y2, we would graph the carrying capacity divided by 2 and find that point of intersection. Well, now, through this very laborious process, we were actually able to show that the inflection point on a logistic, any logistic, given y equals c over 1 times a e to the minus bx, that inflection point on this graph occurs when x equals the ln of a over b. And what's the y value at that point? Well, we just proved ln of a over b that this is going to be c over 2. That's kind of cool. Like, maybe I don't have to do that graphing of this and that y equals line. I could just figure out what a, b, and c are and plug them in. Yeah, it sounds really good, but we're not going to do enough with logistics to make memorizing that worth it. But I really wanted to take the time to just go through something hard with you. There's nothing like that on the tests. There's nothing like that on the AP exam. But I do think it helps you to understand where things come from. We might have said in pre-cal, this is y equals L, and this is always going to be L over 2. And you were just asked to accept that on faith. And now I'm trying to pay back some of that faith by showing you where it came from, and pay back some more of it by saying you'll never have to do that. Okay, so let's take a look. I want to do another table problem. I've got 2 and 3 and F, G, and F prime, and E. And I've got 8, 3, 3, -4, 1/3, pi, -3, pi. So, if y equals 4 f of x, please find y prime of 3. Please don't use the product rule. Please don't use the product rule. It's a constant times a function. Y prime is going to be the constant. It's the derivative of a function. I want y prime of 3. That's 4 times f prime of 3. F prime of 3 is 2 pi. 4 times 2 pi, 4 8 pi. All right, you do the next one. Here we go. Y equals f of x times g of x at x equals -2. Positive, positive. What we're looking for. Please find y prime at, let's use this x equals 2. I want to evaluate this derivative at y. Pause the video, give it a try. Okay, so I like to think you saw product rule. This times the derivative of that plus this times the derivative of that. And I want y prime of 2, so that's going to be f of 2 times g prime of 2 plus g of 2 times prime of 2. Okay, f of 2 is 8, g prime of 2 is -3, g of 2 is 3, f prime of 2 is 1/3. So -24 plus 1 is going to be -20. So I'm saying y prime of 2 is -20. Yay. Okay, a couple more of those. Can you find me, please, y prime if y equals f of x over g of x at x equals 3? Welcome back. Oh, by the way, if you pause the video then, why don't you pause it now, do the problem, and then come back. Alright, now really welcome back. Y prime will be low d high minus I d low all over low squared. So if I want y prime at 3, that means I need g of 3 times f prime of 3 minus f of 3 times g prime of 3 all over g of 3 squared. G of 3 is -4. F prime of 3 is 2 pi. This minus sign. F of 3 is 3. And g prime of 3 is 5. What did I miss? G of 3 is -4. F prime of 3 is 2 pi. Minus f of 3 is 3. And g prime of 3 is 5. Okay, so that's minus 15 minus 85. Good, that's on top. What about on the bottom? G of 3 is -4. -4 squared is positive 16. So I end up with negative, I don't know, 85 first, over 16 is 1 prime. Alright, a couple more of these. How y equals f of g of x, like y prime and this is a very standard stop question. Definitely something you should expect both on our test as well as on the test. So, welcome back. Y prime over outside low times the derivative inside. We want to know y prime of 2. So that means we need f prime of g of 2 times g prime of 2. G of 2? G of 2 is 3. f prime of 3. F prime of 3 is 2 pi. G prime of 2. G prime of 2 is, looks like a negative 6 pi. How about, just one more of these. How about y equals square root of f of x? And I want to know y prime. Welcome back. Did you get y prime equals 1/2 f? Leave that inside alone. To the minus 1/2, don't lose that power, times the derivative of the inside function, which is called x. So y prime of 3 is going to be 1/2 f of 3, the negative 1/2, times f prime of 3. Ooh, I seem to have relieved from the table. I'm glad I still have it on my notes. I guess this will be the last one we do. So I'm looking for f of 3. F of 3 is 3 times f prime of 3. Prime of 3 is 2 pi. So I get 1 over 2 square root of 3 times 2 pi. 4 pi over root 3. And if you're an old school rationalizer, you get pi root 3 over 3. But really, who the hell cares about this? This is fine. We don't use slide rules anymore. All right. So you need to be able to go from a table. You also just need to be able to mechanically find a derivative using chain rule after 3 days of doing chain rule. So find y prime. Quick, hurry. Derivative of tangent is secant squared, leave the inside alone, times the derivative of the inside function. This is not a product rule. It doesn't say tan x times sine x. It's tangent of sine, right? It's not multiplication, it's composition. Tangent had a big lunch. Tangent ate sine x. So this is my chain rule problem. Chain rule is used whenever we have a composition of functions, one function inside of another one. Okay, how about this one? Secant of cotangent x. So then y prime, what's that going to be? What's the derivative of secant? Please don't write this for this problem, because the derivative of secant of stuff is secant stuff, tangent stuff. So I really need secant of cotangent x times tangent of cotangent x. Okay, are we done? No, that was just the derivative of the outside. Now we need the derivative of the inside, which is negative cosecant squared x. All right? Okay. I feel like there was something more I wanted to do with that. I took the derivative of the outside function and I multiplied it by the derivative of the inside function. No, that looks great to me. But really, a lot of people, yep, they leave those out. They just put x's in those places. The derivative of secant of stuff is secant of stuff times tangent of that stuff. And remember, this is not tan x times cotangent x, because you know tangent x times 1 over tangent x, and that becomes 1. Yeah, this isn't that. That's multiplication. This is composition. See, there's no x next to this tangent? That's because this has been put inside of that x. This is not a multiplying problem. I cannot turn that into 1. Okay. How about this one? Y equals 3x minus 5 over 4x plus 1, all raised to the positive 3. Go for it. That's a positive 3. Okay, so what's y prime going to be? Bring down that 3. 3x minus 5, 4x plus 1, subtract 1, times the derivative of the inside. So I think I'm just going to use quotient rule. Low d high minus high d low. I really will strongly encourage you to embrace parentheses up here because this 3 has to be multiplied to each of those, and this negative has to go to each of those. This 4 has to be distributed in as well. Okay, but remember, we're doing quotient rule, 4x plus 1 squared. Now again, on AP free response, leave it like this. No, really, leave it like this. Don't combine like terms. You lose the answer point if you tidy this up incorrectly. Why lose that answer point? Why even risk losing that answer point? Just stop. Now, I will say, if this problem shows up on multiple choice, well, certainly need to tidy this all up. And second, your professor in college, yeah, they're going to say, get out of class if you do that. But for College Board's AP Calculus exam, leave it here. You have enough things to worry about. Don't risk the sign mistake. Okay. Hi. One or two more? Okay. Y equals sine of tangent of square root of cosine x. Hubba hubba. Oh, I do miss my grandmother at times. Okay, give it a try. 4 links in your chain. Welcome back. Y prime, derivative of the outside. Leave all that inside stuff there. Times the derivative of that next innermost function. Derivative of tangent is secant squared. Leave all this stuff alone. Times, now the next innermost function is not cosine, it's the square root. 1 half, leave the inside cosine alone. Don't forget that minus 1. And then finally, times the derivative of the innermost function minus sine x. No problem, piece of cake. You need to practice these until they become no problem, piece of cake. Okay. Wow, I got a bunch more of them. How much is this one? Y equals square root of 1 plus tangent squared x. Okay. So then a lot of people do 1 half, 1 plus tangent squared x to the negative 1 half, and then they come back and they take the derivative of this inside stuff. Derivative of 1 is 0. It's not the derivative of tangent, it's the derivative of that squaring. So, and I know it's strange, but a lot of people get lost right about here. This was 0 plus the derivative of that, 2 10x to the 1. This only times the derivative of that inside tangent function. Okay, now I don't really need that, do I? Okay, and that. Huh, okay. Well, here's what I remember. Isn't that something? I've got 2 tangent x, secant squared x. This is the stuff on top. I have a 2 on the bottom. And then I have this square root of 1 plus tangent squared x. Well, at least we cancel. 1 plus tangent squared? Do you remember? Secant squared. Square root of secant squared? Secant. I get 10x. The derivative of this is 10x. Well, I kind of want to do this problem another way. It really sort of pays tribute to what we did last January in trig class. We have this Pythagorean identity sitting right in front of us. And I'm talking about secant x squared, and then I'm taking the square root of it. So y is really just secant x. So then y prime, well, that's secant x, tangent x. Uh-oh, we got tangent x before. You mean I did all that work wrong? Yeah, actually. Did you find the mistake? Did you see me make it? Go on, let's find it together. Okay, so we've got 1/2. This is 1 prime, not 2 primes. Leave the inside alone. Minus 1/2. And then we came back and we took the derivative of the inside. The derivative of 1 is 0. The derivative of this was 2 tan x. Yes, to the 1 times the derivative of tangent x, which is secant squared. Okay, do I have all the bits? Took the derivative of the outside, I left the inside alone. I took the derivative of the 1. I took the derivative of squaring and I left the tangent. And then I came back and took the derivative of tangent. All right. So on top, 2 tan x secant squared x. Oh, I only wrote it as secant x. 2, no, yes, 2 from this 1/2. And then we have square root of 1 plus tangent squared. That's secant squared. Square root of secant squared is just going to be secant. And so that cancels one of those. These cancel. And we end up with tangent x, secant x, which is in fact the derivative of secant. So that tells me that all this stuff is really just secant. Okay? All right. Last thing I want to look at with you today, remember the table problem? But wait, now we get this problem. Okay, there and there. This point is 0, 3. This point is 1, 2. This point is 2, 1. This point is 3, 0. Over here, I have 4, 3. And then out here, I seem to have 9, 6. This is a graph of f of x. Now, in a different color, let's write a graph of g of x. I think this is g of x. F is in there. Okay, so we're going to pass through this point, and we're going to go up to here, and then come across. So, oh, well, that's weird. So the point isn't labeled that way, so I'm going to change that a little bit. But this is still 1, 2. And then we get to this place here, 2, 4. And we get to this place here, 3, 6. And then we come across, and we stop at 5, 6. So it doesn't go all the way across to that. Okay, and that's a graph of g of x. And also 0, 0. Okay, so we've got this f, we've got this g, and now we're asked about some things. What things? Well, let's say h of x equals x squared times g of x. And I'd like to know what h prime of 1 is. This is so popular on the AP exam these days. I mean, like, guaranteed gonna see it. So I see a product. Use the product rule. 2x times g of x plus x squared times g prime of x. Now that's not h prime of 1, that's h prime of x. You really have to pay attention to details like that. H prime of 1 is going to be 2 times 1 times g of 1 plus 1 squared times g prime of 1. This step here, many of you don't want to do it. And actually, I've seen a lot of students who got stuck. Like, I have no idea how to figure this out. And so I find writing down h prime of 1 reminds me of x. x's and h prime of x with 1s. So g of 1 is g of x, g of 1 is 2 plus g prime of 1. Well, doesn't that mean the slope of g at 1? Not the y value of g, the slope. How can I not slope? Look, 2 ordered pairs. So 6 minus 0 over 3 minus 0 is 6 over 3, which is 2. So g prime at 1 is 2. G prime anywhere on this segment is 2. On this segment, g prime would be 0. Okay, so I've got 1 times 2. 4 plus 2, 6. H prime of 1 is 6. Excellent. Now I think you know what I'm going after here. So will you please find, given that h of x is g squared of x, please find h prime of 3. Okay, pause the video, give it a try, come back. Hey, welcome back. Did you find that h prime of x was 2, leave the inside alone, times g prime of x? And so then h prime of 3 is going to be 2 times g of 3 times g prime of 3. G of 3, there's the g graph, g of 3 is 6. G prime of 3. Whoa, why did I do that? Well, here's g. There's g prime. Does g prime exist? Doesn't exist. From the positive side, g prime is approaching 0. From the negative side, g prime is approaching 2. And 2 doesn't equal 0, so there can't be a derivative there. Oh, how sad. That's right, you're not allowed to forget the old stuff. Good. So, does not exist is what we write. Okay. And I don't necessarily know that here. I mean, if I thought about it a whole lot, I'd say, well, yeah, I know. Because I'm wondering what the g squared graph looks like. But when I just compute the derivative and plug my 3's in, I know I can't have a derivative there or a derivative here. So f of prime of 3 isn't going to exist either. All right, how about this? Y equals g of x squared. Last time we did g squared x. We had the g on the inside and the squaring on the outside. Now I'm putting the squaring on the inside. So, show me what you get. Welcome back. So we know that's going to be g prime of x squared times the derivative of the inside function. And if I'm looking for h prime of 2, I guess y prime of 2 is 1. What's that going to be? Well, that's going to be g prime of 2 squared times 2. I have no place to put x. G prime of 4, what's the slope at 4 on g? Here's 3, here's 5, so here's 4. What's the slope on g at 4? Slope there. You should have done a horizontal tangent. So we end up with 0. Okay. How about just 2 more problems? Just 2. How about h of x equals f of g of x? You know, this is really 3 days about chain rule, so it makes sense that we wrap it up with chain rule. I've now erased the graphs, so don't worry about it. I'll do this one. F prime g of x, and I want h prime of 2, which is going to be f prime of g of 2. When I look on the g graph at 2, there's a y value of 4. F prime of 4. Well, the slope at 4 on f. Well, I see this point here 0. And I see this point here at 4, 3. So 3 minus 0 over 4 minus 3. It looks like the slope here is 3. So the slope on f at 4 is 3. Welcome to your knowledge of chain rule. Now, if you're not really comfortable with chain rule right now, really, you need to do about a bazillion more problems so that you can be comfortable with chain rule. You really do need to be comfortable with chain rule. You really do need to do this practice. Please. Okay? Well, have a wonderful day, everyone. I hope this was helpful. I hope you're feeling more confident with chain rule. Take care.